announcements. All right, here we are. Hey, folks. Welcome back. It is Thursday. All right, this is that's our final class of the week. Today, in today's lesson, we're going to wrap up what we want to do for chapter 13 with finite automata and language recognition. Next week, you will have your last quiz. That quiz will cover what we did for chapters 9, 10, and 11. This more recent stuff on finite state machines and like formal languages, I've decided that's not going to be on the quiz. So next week, we will return to those topics from 9, 10, and 11 and do a little bit of review before you quiz on Wednesday. Okay. As always, we'll be continuing to work on the project. Okay. Next week is the last week before our final project presentation. So if you want to show me your project again to get a little bit of feedback, send your video to me, send your slides to me, anything like that. Please feel free to do that, and I'll find some time to take a look and get back to you. Does anybody have any questions before we get started? Well, all right, so I'm going to draw, or actually, no, I'm not going to, we're going to do a couple of examples of finite automata first, just to kind of warm up here. So first, let's make a finite state automaton, which we'll abbreviate FSA, finite state automaton, to recognize the set of binary strings that end with the sequence 1101. Yesterday, or not yesterday, but 2 days ago, we did an example of a finite state automaton that recognizes binary strings that contain 1101 as a consecutive substring. Today, we're going to look at, so for this one, we're going to modify that approach a little bit and say, well, what if we want it specifically to end with 1101? Well, we're going to have an initial state, and we're going to be searching for the 1, 1, 0, 1, right? And if it ends with 1101, we're going to accept our string. So let's label these state 1, state 2, state 3, and state 4. Okay, if it ends with a 1101, accept it. But after it reaches that 1101, if it gets another input after that, if it gets, say, a 1, it would have to go all the way back to the beginning. If it gets a 0, all the way back to the beginning. Because either a 1 or a 0 would interrupt that string, right? Now, is this right, what I did here? Do you guys agree? It should go all the way back to the beginning if it gets a 1 or a 0. Uh-oh, see a no.
Wait, no, I'm wrong. Wait, if it gets a 1, shouldn't it go to the second step, not the first step?
Why? You mean like this?
Yeah, because it's going to be restarting the sequence.
Ah, very good. Yes. So, so you might think, so I kind of intentionally made a mistake there, guys. You might think, oh, if it gets anything, it interrupts the chain and it goes all the way back to the beginning. That sort of makes sense, except that if it does it with a 1, then actually it's like that could be the first number in the new string, right? Is that correct? Is it correct now? Still not quite correct, actually. Why, John, you say it's not correct. Why isn't it correct, John? You think it should go back to state 3? Let's adjust this. If it gets a 1, should it go back here?
No. For the 0, wouldn't you want to go back to like state 2 or 3? It's one of the two. I think it's 2.
Oh, the 0? Okay, so if we had a 1, 1, 0, 1, and we thought that might be the end of the string, but then we received a 0.
Oh, never mind. Yeah.
The 0 really does reset the whole thing.
Yeah.
I think this part is correct. I would say that part's right. But this one is this. If it receives a 1, this is not actually correct. We don't want to go back to state 1. We can do better than that. Connor says it should go to state 2 if we receive a 1. Okay, Connor, why does it go to state 2?
Because as we entered from state 3 into state 4, we already have a 1. So that's like going from state 0 to state 1. So now that we have another 1, it's like going from state 1 to state 2 all over again.
There we go. Yeah, that's right. It's like we just saw a 1 in the string. We just read that 1. So this 1 is equivalent to this 1, right? And then this 1 would be like equivalent to this 1. And so if we see that 1, it means we go back to state 2 because we just read a 1. So now we're back at the situation of having read 2 1s in a row, which could be the beginning of the first two characters in the 1 1 0 1 sequence. That's right. Wow. Okay. Cool. Yeah. So that was a little harder than we might have thought originally, right? But now we have the beginnings of our finite state automaton. Now there's a little bit to fix up here, which is there's a few things we need to add in. What if right away we receive a 0? From the very initial state, if we receive a 0, we can essentially ignore it, right? And loop on that state. Say, hey, let's just ignore that 0. That's not the beginning of our sequence pattern we're looking for. There we go. If you receive a 1 and then you're in state 1 anticipating the second one, if at that point you receive a 0, that resets you as well. So the 0 resets, right? Back to there. And then if you're in state 2, when you've received 2 1s and you're anticipating a 0, if you receive a 1, like we discussed on Tuesday, we want to loop right there because that double 1 in a row is equivalent to this double 1 in a row or this double 1 in a row. So state 2 is the state to stay in when you've got 2 1s in a row, right? 2 or more 1s in a row, I guess it is. Are we missing anything else? I think we're missing one more thing, which is when you're in state 3, what should we do if we receive a 0? What do you think?
You need to reset.
Reset again? Yeah, I think that's right. Yes, reset. Go back to the start. 0 right there. Woo! All right. Cool. I think that's done now. I think we've got all of the 1s and 0s accounted for. When you're building a deterministic finite state automaton like this, just make sure that from every state you have exactly 2 arrows leaving that state, right? So exactly 2 arrows, one with a 1 label and one with a 0 label. Okay, so that way we know exactly what to do no matter what state we're in and whatever and what input we read. You don't want to accidentally make it so that there's 2 instructions for the same input, right? So if you said go back to the start with the 0, but also go back here with a 0, you can't do that because then the function isn't well defined. Remember that a function has to have one and only one output for every input. Okay, we can't be doing that. That's like saying f of 1 equals 2 and f of 1 also equals 8. It's not a function if you do that, right? So there's our first example. Now for the second example, I want to draw a finite state automaton, and we're going to practice interpreting that automaton to figure out what is the set that it will recognize. All right. So there's the finite state automaton. What the heck is it doing? What is it doing? What is its job? What type of strings, binary strings, will be accepted by this machine? Meaning, what type of strings will cause the machine to halt, which means stop because it doesn't have any more inputs to read, in an accepting state. The only accepting state is state 3 right over here. So which strings will it accept? Think about that. I'm going to grab my cup of coffee. I think I seem to have misplaced my coffee. While you think about that, I'm going to go get my coffee. All right, what's up? Cameron, you got a hand?
Right, just to clarify, this is asking us what it's looking for?
Yeah, what is this machine going to, what strings is this machine going to accept? Right? Like accept meaning it gets, it ends in state 3 in this case. Philip's given us a few things. 0, 0, and 1, 1 would be 2 examples of strings that it would definitely accept. But that doesn't cover everything. So, okay, here we go. So Connor has has sort of expanded on that answer to say not only will it accept these strings, I'm looking at the chat here, we could also do 0 and then 1 to the n, followed by another 0. Or we could do 1 and then 0 to the n, followed by another 1. So remember, 1 to the n, 1 to the n means n copies of 1 concatenated together or strung together. So like 1 to the 0 is just the like empty string. 1 to the 1 is just 1. 1 squared is 1 1, and 1 cubed is 1 1 1, etc. Okay. So this basically means between the zeros, we could have any number of 1s, and between these 1s, we could have any number of zeros. Well, that makes sense here. We've got our 0, any number of 1s would just loop because we would basically ignore those 1s, right? And then we've got our second 0. If we start with a 1, we could have any number of zeros, and then we have our second 1, right? After we receive either the second 0 or the second 1, we're accepting, but any further characters in the string would take this machine to a pit of despair. right here, right? From which we can never return, right? And it'll be like rejecting forever because we just loop on zeros and ones at that point. So is that it? Is this it? Does that describe all of the accepted strings?
Don't you technically have a string where it goes O1N, O1N slash O? I'm thinking about the permutation here because in the pit, technically the pit's a unification point. So can't you have like a 1 O to the N, 1 1 to the N kind of string?
No, because if we had 1 and then 0 to the N, so any number of zeros, and then a 1 to the N, then we could have further ones. And if we have another 1 after this one right here, then that would take us along this transition. We would be then in state 4. State 4 is a rejecting state, and then we can never leave state 4 because 0 and 1 simply loop on that state. And so it would be rejected. Does that make sense? Yeah. So once we receive this one right here, we can't have no further characters in the string. Like it has to be that would have to be the final character in the string. Or alternatively, if we had started down this path, the 0 would be the final character in the string. Yeah. So these are the only two things we could have. So the way we could write this is L of M. So if this is machine called M, the language generated by this M is the set of anything of the form 0, 1 to the N 0, or, which we can just do comma, 1, 0 to the N 1. And that is where N is any natural number starting at 0 and going up with whole values from there. So that is how you can write that language in set builder notation. Okay. So now that we have introduced, now that we've gone over those two examples, let's do some other things. So let's formally define something that we've been talking about here. And that is a string W is recognized or accepted by a machine if W takes the starting state S0 to a state in F, which means an accepting state or final state, as it is sometimes called. Remember that F is in the definition of the machine, right? We have the set of states, the set of inputs, the function, the transition function, the starting state, and the set of final states, which are the accepting states, right? So that's the formal definition that we're working with here. And then we can say the language recognized by the machine is the set of all such strings. And this is a formal language. Okay. So back when we defined what formal languages are, we said a formal language is technically, a formal language could be any subset of the set of strings over the alphabet. So here, the language generated by the machine, M, is denoted like this, L of M, the language generated by the machine M, or actually the language recognized by the machine M. I haven't introduced the word generated, but we're going to talk about that in a second. And that is going to be a subset, a subset of the set of all possible strings over the input alphabet. So whatever that input alphabet was, that set I I star is the set of all strings over that alphabet, and L of M is just some subset of that. Okay, it's a formal language using I as its alphabet. Now, I've been using the word recognized and generated kind of interchangeably, and I wanted to explain that because there's this sort of question of origin. What is the origin of this formal language we're talking about? Is it that and actually this goes back to the way that we approach these examples. Is it that the formal language has been established already, and then we are just building a machine to recognize that formal language? Or is the machine something that we have built, and now we are just determining what is the language associated with that machine? So where is the origin of this language? The machine can be thought of as either recognizing some predefined language or generating a new language by virtue of the strings that it accepts. Okay, so that's why a lot of times I'll say the language generated by the machine. It's like you can kind of think about it either way. Does that make sense to you guys? They're equivalent, so it's not like it has to be one way or the other. It's kind of both at the same time. All right, the machine both defines the language and also like can like recognize the language if it's been defined. Anyway, this notion of the language generated or recognized by a machine also gives us a way to define equivalence of finite state automata. We can say two machines are equivalent to each other if they generate/recognize the same language. So that basically they accept the exact same set of strings. I guess I don't have an example off the top of my head, but you can make machines in different ways that that look different. They have different states and different transitions, but they still recognize the exact same sets. We could go into an example. I guess I'm thinking about it now as I do this, and I'm thinking it would be pretty easy for me to make an example of that on the fly if you wanted to see it. So we could do that. Let me know if you would like to see that. All right, we're going to go to a new page. Question: what type of languages can be generated by finite state automata? Is it just anything? Okay, can you pick literally any subset of the set of strings over an alphabet and design a finite state automaton to recognize that? Is it any language? No. The answer to that is no. Finite state automata can recognize/generate only regular languages. This is the terminology. The type of languages that finite state automata are capable of generating are called the regular languages, okay, i.e. regular sets, okay. Okay, this is proven by a guy named Stephen Kleene in 1956. And that's called Kleene's theorem. And we're going to build up to Kleen's theorem over the next few minutes, next 5 to 10 minutes here, okay? But before we can state Kleen's theorem, before we can, what we need to get back in and develop an understanding of this term. Okay, so we're going to define regular sets, and then we can state Kleen's theorem, which is about regular sets. Okay, so backing up a little bit, we need to talk about operations on sets of strings. Operations on sets include things like union and intersection. Operations on strings include things like, well, there's really only one meaningful operation on strings that we've even dealt with, and that's the concatenation operation. If you have a set of strings, you can define operations on the set of strings either with set operations or with string operations. So it's kind of like a combination of the set operations and the string operations. So we have union. Oh, hang on a second. We'll first, suppose that A and B are subsets of some alphabet set of all strings over that alphabet. Okay, so A and B are subsets of set of all strings over the alphabet. So the alphabet is called I. I'm using I because for finite automata, it's I. It's I for input alphabet. I star, right? So for example, if the input alphabet were just 0 and 1, the Boolean values, right? Then we could have things like A is the set 0, 1 and 1, 1, 0. And B is the set 1, 1, 1 and 1, 0, 1 or something. Those are finite. They don't actually have to be finite. A and B could be infinite. But the point is they're just some set of strings using the alphabet I. Okay, so operations, you can have union, which is exactly what you'd expect. It's the union of the two sets. And you can have intersection, which is also exactly what you expect. So in my example over here, the A union B would be the set of all strings that include things from A or things from B, right? Which would be that. And the intersection in my example here would be just the empty set. Okay, so denote, remember, empty set is denoted like that. Okay, so we've got intersections and unions. And then we have concatenation. Concatenation, we've defined it for individual strings, but now we're going to define concatenation for sets of strings. And concatenation is denoted like that, just straight up juxtaposed, set A, set B. And it is defined as the set of all xy, where x is a string from A and y is a string from B. Okay, so in our example over here, AB would equal a lot of things, actually. We could do something from A, like 0, 1, followed by something from B. Let's have B be in red, just to distinguish them. Or we could have 0, 1 followed by something else from B. Or 0, 1 followed by some other thing from B. We have all of the different possibilities of taking 0, 1 and then following it with some string from B, right? We do that for every one of the strings in A. So there's another one. And there's another one. Oops. And there's another one. And that would be the entire set A concatenated with B. It's just all the things you can get by concatenating something from A with something from B. So it's sort of similar in some ways to a Cartesian product, A cross B, in that if everything, it's sort of like, actually doesn't even, yeah, the size is just going to be the number of things in A times the number of things in B. If those are both finite values, it's just the product of the cardinalities, right? Because it's like how many choices of an A string do you have times how many choices of a B string do you have? Okay, so it's just that instead of putting them together into an ordered pair, we're putting them together into a concatenated string, a longer string. Okay. So that's concatenation. Then we can extend the idea of concatenation by powers. A power of a set of strings, which is defined recursively like this. A to the power 0 is lambda. And then A to the power n is A concatenated with A to the power n minus 1. And that's a recursive definition. So from this, we can obtain A to the power 1 is A concatenated with A to the power 0. In other words, A concatenated with the set containing lambda. And if you concatenate everything in A with lambda, when you concatenate with lambda, you just get, it's like an identity operation. It's like adding 0 or multiplying by 1. And you just get the same thing you started with right back again. So the result of this is just A. So A to the power 1 equals A, like we would want. And then A squared is going to be A concatenated with A to the power 1, which is A concatenated with A. And A cubed, as you can probably guess, is going to be A concatenated with A concatenated with A, and so on. So you can have successive concatenations of things from A with other things from A, and building up with any number of those, So like if you have A to the power 4, it's like all of the possible strings you can get by taking 4 strings from A and concatenating them together. And it could be the same exact string chosen 4 times, or it could be 4 distinct strings, or some combination thereof. Okay. So that's the power function. And then taking that power function to the extreme, we get what's called the clean closure of the set. This is A star, which is sort of like A to the power infinity, but not exactly. What it is it's a union of all of the powers of A. So union over K going from 0 to infinity of A to the power K. So this is, in other words, the set of all strings of strings from A, from the set A. The set of all strings of strings, okay, of any length. So for example, an example of clean closure. If we take our set A that I defined over there, which is 0, 1, and 1, 1, 0, okay, then A star will equal A to the power 0 union with A to the power 1, union with A squared, union with A cubed, union with A to the power 4, etc. forever, right? Union from 0, to infinity, all of those powers of A. And so what this will contain is lambda. A to the power 0 is lambda. A is just 0, 1, and 1, 1, 0. A squared is going to be 0, 1, 0, 1, which is like 0, 1 concatenated with itself. And then you could do 0, 1, 1, 1, 0, which is 0, 1 concatenated with 1, 1, 0. And then you could do 1, 1, 0 0, 1, which is the second concatenated with the first, or you could do the second 1, 1, 0 concatenated with itself 1, 1, 0. So that all the 4, that's all a squared, right? And that's just a squared. And then you do a cubed, and a cubed would be the set of all, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, and 0, 1, 1, 1, 0, 1, 1, 0, and blah, 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 blah. I'm not going to write that all out because that would be pretty long. In fact, I guess it would be 8 different strings because it's 2 strings to the power 3. 8 different options, right? So all of these sets together is what A star is. So it has all of these things. Now, since A only contained these chunks, these like strings of 0, 1 and 1, 1, 0, there's things in its clean closure, or there's things that aren't in its clean closure. So like, for example, 1 by itself isn't in the clean closure of A, because you can't construct the string 1 by taking things in A concatenated with other things in A, right? You also I also don't have the string 1, 0, 1, right? So like 1, 0, 1 is not an element of A star because there's no way to make 1, 0, 1 by taking 1, 0, 0 1s or 1, 1 0s and combining them together, right? The only things that are in here are things that you can form in combinations of 1, 1 0s and 0 1s. Like that. Okay. So when we used this star notation to denote like the set of all strings over an alphabet, technically that is a clean closure. If you view the alphabet as a set of strings of length 1, it's like singletons. It's like a set of singleton strings, right? If a character is considered a string of length 1, then you can call that a clean closure and you get the set of all strings of those characters. It's just the clean closure could also be applied to a set of strings, not a set of characters. Does that make sense? Okay. So these are the operations we need to talk about for sets of strings. So now we can define what a regular set really is. And for that, we'll use what are called regular expressions. And actually, I'm going to stay on this page for a little bit. Regular sets are defined by regular expressions. And it's a recursive definition, again. Okay, and here's how it goes. The empty set is regular. Lambda is regular. Okay, and I want to make, and this is a bold face lambda. Bold lambda. The bold characters that are used in regular expressions are used to denote a set containing that single string. So a bold lambda would represent the set containing lambda. So that is regular, okay? X, bold X, is regular for any X in the alphabet. We're going to use the I to represent our alphabet we're working with here. Okay, so that's bold as well. So there, that bold X represents a singleton set containing X. Okay, like that. And then these are all the base cases. These are the base cases, okay? Oops. Base cases. And then we have the recursion rules. And the recursion rules, there's 3 of them as well. And they say, if A and B are regular, then so are A union B, A concatenated with B, and A star. And B star, I guess, but it kind of goes without saying. So basically, whenever you have a regular set, or whenever you have a regular set, its clean closure is regular. And whenever you have 2 regular sets, their union is regular and their concatenation is regular. Not intersection, but union and concatenation. So so these are the definitions of regular expressions which define regular sets. So we can look back and say, hey, remember that set which we described as 0, 1 to the n, 0, or 1, 0 to the n, 1. Remember that set where n was like any natural number? We can describe that set with regular expressions by saying it's 0, which is bold, concatenated with 1 star, okay, bold 1 star, concatenated with 0. So here we have bold 0s and 1s, which represent like singleton sets, okay? And then we're combining them using the concatenation operation here and here. And this 1 star is, we have a clean closure, which means that it could be lambda, or it could be 1, or it could be 1, 1, or 1, 1, 1, or anything like that. And then we have all of those union with the other set of possible things, which is 1, 0 star, 1. Like that. And that is a regular expression which defines a regular set. Okay. And that's just an alternate notation for the same set we did with set builder notation earlier. Okay. So there we go. So Kleen's theorem actually just, oops, no, it's the wrong thing. Kleen's theorem actually just says that the set of, like the type of languages that you can generate with a finite automaton are just the regular sets, regular languages, okay? Those which can be described using regular expressions. But this is not all possible sets. There are sets that are not regular. So the way I want to finish class today is with an example of a set which is not regular. And it's a set that we have talked about before. It's this set. It's the 0 to the n, 1 to the n set, where n is a natural number. So this set contains things like lambda and 0, 1 and 0, 0, 1, 1 and 0, 0, 0, 1, 1, 1 and so on. 0, 0, 0, 0, 1, 1, 1, 1, etc. It's important for the definition of this set that the number of zeros be equal to the number of ones. So let us be very clear. This is not 0 star 1 star. Because 0 star 1 star contains things like, contains strings such as 1 or a 0, 0, 1, 1, 1, 1, 1. The number of zeros need not equal the number of ones in the 0 star 1 star regular set. That makes sense? Those are not the same thing. This is not regular. Quick explanation of why. Basically, you can prove this by contradiction. You can say, if this 0 to the n, 1 to the n is regular, then there must be a finite state automaton that recognizes that set. But how would you just describe, how would you create such a finite state automaton? You'd have to say, every time you see a 0, take note of the fact that you saw a 0. And we need to somehow count the number of zeros. Right? Count how many zeros are read by the machine. And then at some point, we would need to transition to some states where we are viewing a 1. And then read ones. Read more ones. And keep on reading ones until we reach some final state 2n, where we can finally say, ah, yes, now the number of zeros which have been read is equal to the number of ones which have been read. Count how many ones are read to make sure it's the same as the number of zeros. But you need this machine to work no matter how many zeros are read in the beginning, in the first part of the string. Like if it reads 3 zeros, you need it to count 3 ones. If it reads 12 zeros, you need it to count 12 ones. But how many states will this machine have? It's a contradiction. Okay, I'm not going into the rigorous detail because we're out of time, but there ends up being this contradiction here where it's like you can't make a finite state automaton that does this because there's no way to know how many states it should have. And if you say it's going to have this many states, you can derive a contradiction from that, where you end up being able to recognize, you end up showing that it has to be able to recognize strings that shouldn't be in the set. Contradiction. So this is just one example of a non-regular set that a finite state automaton cannot generate or recognize. So that's it, folks. If you got to get going, please go ahead and head out. Before I stop recording, I will answer Ben's question. Regular expressions can be used to search. So one of the primary applications of regular expressions is searching for things, like searching for patterns. Because you can interpret a regular expression as essentially describing a pattern, a type of string. And so this is the same regular expressions that is applied over there. It's the same concept The notation that's used in this textbook might be a little bit different than the notation you're familiar with from other languages, but it is the same idea. Okay. So that's it, folks. We will see you next week.